cosmology release of the Planck satellite. This has been in production for about 20 years, and as you'll see, is now releasing the first of what will be several cosmology releases. So what you'll see today will not be the full data set that we have in the can already, and more is coming into the can, but it will be a significant release. Peter Meinhold has been working on this project for 17 years now. It's a long time. And Andrea Zonka is a postdoc with us, who's been working for quite a while on the project. And Tila Vanderveen has been here for more than 20 years. And she's been working on the project as the program manager for education public outreach. So this data set is quite significant. There are a number of issues related to both the quality of the data set and what it says, in addition to the standard models. There are some interesting anomalies that might be indicative of new physics. It's unclear. So we're going to do this in rotation so that everyone gets a chance to talk. It's probably best if you could hold the questions until the end. And there'll be a time for discussion. Okay, so
so what you're looking at is the foreground removed CMD map from Planck. This is one of several different CMD maps that are available. This is just the previous one. So the first cosmology release is today. We're all excited. You all should be too. The papers that are out are available at all these different sites. There are 29 papers coming out right now. The maps are available, and I'll describe what other products are available. But everything for doing your own cosmology is now available in Planck data. As Phil said, these are the people that are involved in Planck at UCSB. We've been working here on Planck since 1996. I don't know if Andrea was born in 1996, but we're all of us. This is the four of us, and then Greg Dobler, I don't think he's here. So before I take you through all the boilerplate that you have to sit through, I thought we'd go through the highlights so that people don't have to wait. Probably a lot of you who are here already saw this on the news, but this is how we put it. So Planck firmly established a deviation from scale invariance. In other words, NS is not 1. They're pretty high simultaneous. We'll talk about that more later. We detect lensing of the CMD by intervening matter with high significance. It's a beautiful lensing map that's going to be part of the release that could be used for lots of other physics, but it's independent in confirmation of dark energy, CMD alone. Planck finds no evidence for significant deviations from Gaussianity in the statistics of CMD anisotropes. So it's a boring answer, but what can we say? This is the universe we have, and that's the answer so far. Planck finds a low value of the Hubble constant, which is going to, I think, launch 1,000 papers, extension with the value derived from the standard distance ladder. Again, we'll have some figures about that later. Planck finds a deficit of power at low L with respect to our best fit model. This is becoming it's an interesting thing to talk about without an interpretation of the best fit model. Planck establishes anomalies at large angular scales, and we'll show some plots of these. They may be interesting, and they may tell you something about the universe, or they may just be blemishes on the universe. We'll see. And Planck establishes a number of interesting species at 3. And now this is what LFI, the low-frequency instrument in Planck, looked like when we started working on it in circa 1999. This is over in Beretta Hall, the basement, one of our first floor labs. This is what it looked like just before it launched in 2009. And the radiometers are in here, and the bolometer instrument. And reflected in this mirror, you can see, this is the primary mirror, you can actually see the Herschel telescope, which launched in the same rocket, just across the high bay. I'm not going to spend too much time on this, because after we made it to the rocket, we launched in May 14th, 2009. And I'll French it down. Talk about this for a second. Planck is the 4th orbital mission to go after the CMD anisotropy. So It's often said that there are three, but there was actually a Russian satellite that launched in 1983 that successfully measured the dipole component. There was Colloq in 1889, which established the first anisotropies outside of the dipole. WMAP, of course, with beautiful measurements of the acoustic piece, and now Planck. This gives you an idea of the relative resolution of the instruments. And up here, we've put out the relative sensitivity. There's different ways of calculating it, but in terms of sensitivity per unit time, Planck is about a factor of 1,000 more sensitive than WMAP per unit time for ticket detectors. WMAP a factor of 1,000 more than Colloq, and a factor which is quite similar to further comparison to a relative satellite. What this means essentially is that it takes 1,000 years of WMAP to get the same sensitivity for a pixel as 1 year Planck and 1 million years of Colloq. That doesn't have the whole story because, of course, the resolution and the frequency coverage are also great. This is just a depiction so you can orient yourself of what Planck's orbit is. We're at the L2, orbiting around L2 Lagrange point. This is Earth and the Moon. The sizes are not the scale that their orbits are. And we orbit in these kind of lazy Lissajous orbits and travel around keeping the satellite pointed, the rotation axis of the satellite pointed away from the Earth-Sun system, and then we scan out great circuits on the sky and generate our maps that way. It's a very stable place to work. It's the same part of the orbit that we know. So the data that are being released today, have been released today, are from the first 15.5 months of observations. And there are full sky maps for all 9 frequencies. For the first survey and the second survey. There are also what we call half rings. These are extremely valuable for doing systematics and noise analysis. Because of the way Planck scans, we're able to divide the data into 2 independent data sets taken at the same time. So you spend 40 minutes on each position on the sky. And by splitting them into 2 pieces, you can make independent sky maps, which you can then use to measure noise directly, do cross spectra, and so on. Those are extremely valuable. We'll show a little bit of that. But they underpin a lot of the work that convinces us that we understand our data very, very well. There are some component separation maps also being released. CMD maps from component separation, also thermal dust models, and residual cosmic infrared background. There is an ancillary data set, which is a measure of CO in our galaxy, interesting to some people. Synchrotron, free and spinning dust are in a combined low frequency map, and the dust temperature and opacity map that will be released. There's also a low resolution CMD map that's used for low L likelihood, and the likelihood code itself, including a lensing information for the lensing potential, is released as well, so people can do their own cosmology with the Planck data with the proper weighting of the noise and components. There are also 2 catalogs of sources. One is the compact source catalog, PCCS, and then the semi-observable sources, which are very useful. Those are all available right now. This is just a list of all the papers. They're all really great. You should read every one of them. I think it's 700 pages. But you can start with the overview. There's what we call the mission paper, the overview of products and results. It's a summary and it's a roadmap to all of these other ones. So there are people there that want to spend their time figuring out what we did wrong. And so they'll read the systematics papers, and there'll be people that are excited about new cosmology, and they'll read the inflation papers. Everything is there that we understand about Planck at this point, about the release data. This is just a little map that shows you what those papers look like. It's maybe even more interesting after you try and read them. But green refers to processing papers. Pink are the products, so frequency maps, component maps, all the things I just mentioned. And blue are science results based on those inputs. And so this will kind of tell you where you want to go. If you want to find out what we did to remove cosmic ray glitches, and you look in the paper. You want to understand our calibration, you look there. You understand what we say about cosmological parameters. So, one last slide on boilerplate. This is the Planck sensitivity again. I just can't resist pointing out this number. This 17.4 is microkelvin CMD per second. It tells you that in 1 second, in this frequency channel, Planck can measure with an error bar of 17 microkelvin. It's a factor of 1,000 lower than the equivalent number for Colloq, which was a very similar number in non-Kelvin seconds. And of course, we have all this incredible frequency coverage. So now I want to show you the maps and talk about a little bit about them. So this is all the maps are going to be in galactic coordinates. And we have this, what we call the universal color scale at the bottom here. It's quite difficult to display the incredible dynamic range available in these maps when you think about foregrounds as well as the background radiation and the frequency coverage. And so this scale, which is logarithmic and has a various set of colors, covers 7 orders of magnitude in brightness. And it has one thing that's a little bit funny, which is that the 2 highest frequency channels, which are basically insensitive to CMB but very sensitive to dust emission, are given in surface brightness units that are familiar to people who work with the IRIS datasets. So 30 gigahertz. So as I'm going to flip through these a few times, but as you go through it, what you can notice is that the galactic part of this, across the central part and standing up here, changes, goes through a minimum, and then gets completely dominated by dust, which is white here. If we start back at 30 gigahertz again, you look up here, anywhere off the galactic plane, you'll see anisotropies that are just CMD and how incredibly constant they are until they get swallowed up by the dust. I think we're going to talk a little bit about the takeaways from Planck, and we try to put them in a few bullet points. But I think what's really the takeaway from Planck is these maps. These are extremely well understood, extremely sensitive, all-sky maps, a range of frequencies that are of great interest for cosmology and for galactic science, irrespective of the CMB. Even if we didn't have the CMB, we would do cosmology with the results of these maps. And I think it's going to be years before we understand everything that's in them. And they're yours to play with right now. So I'm interested to see what everybody else thinks. In particular, I can point out that at the highest frequencies, when the CMB is not there, not visible, you can still see, you still get to do cosmology because you get to look at the cosmic infrared background, which is what's dominating the signal far up the galactic plane at these highest frequencies. And I just want to show one example of the internal consistency. We're not talking about the details of data analysis here, but this is what you get when you do a half-ring difference. So take half the data from those measurements and subtract it from the other half, and you get this featureless map. The scale here is plus or minus 10 microkelvin, and this has been smoothed to 1 degree just to try and see some features, but you really don't see them. You see a slight change in how much sensitivity we have. The noise is lowered here because it's observed more often. But this sort of lack of features is one way that we know we trust our data, and we use tests like this all the time in the data analysis. You can do a similar thing comparing among frequencies. This is an interesting comparison because the 100 gigahertz is the lowest frequency of the high-frequency instrument, which is a volumetric receiver instrument, and 70 is the highest frequency of the low-frequency instrument. So this comparison is where we cross over. You expect to see, as you do here, the foregrounds in the galaxy are a little bit different. So the dust, which shows up here, is brighter at 100 gigahertz and dimmer at 70, whereas H1 emission is brighter at 70 and is a hunk, so it shows up negative. But outside of that, you see almost no features. There's this one stripe here that everyone likes to point out. We have 2 days of missing data around the start of the mission and when we switched to crowd coolers, and so there's a little less integration time here. So what you're actually seeing is a difference in the noise density here. It doesn't affect the data analysis. Okay, so let's switch over.
Yeah. So Okay, so I'm gonna spend a little time talking about the component separation pipeline and the likelihood pipeline that provides from the input maps at 9 frequencies the products that are available today in the release. So as you see, looking at all the maps together, you can see that the low frequencies are dominated by synchrotron and free emission, and here are what we call our CMB channels, so 7100 and 143, and then the highest frequencies are dominated by dust emission. And we have a pretty complicated pipeline. Now I'm just going to show part of it for extracting, for finalizing the products from these input maps. So here so the starting point is the timelines. So from the orange color here are products that are not released, while in blue are all released products, and in green some external data sets that we use to reduce our data. So from the frequency map, so first of all we have compact sources detection and extraction that produces the catalogs Peter talked about before, and that are then used to mask out the sources. And then we have several types of component separation software we use. So we have a specialized component separation to extract CO. Then we have a pixel-based component separation method that can extract CMB and component maps at different at a very high resolution at 700 minutes. Here you see an output of our component separation pipeline. So on the top we have a low frequency component that contains both synchrotron, free and anomalous emission. Here at the two different type of solutions, so 1 degree and 700 minutes. Then the second component is CO emission, and then the third component is dust. So this algorithm is based on Bayesian parameter estimation using the software called Commander, which runs at low resolution, and then after the component separation has been performed at low resolution, the results of the component separation is used to reconstruct the components at higher resolution. And all of these components are available in the current release. Here, of course, we separating the components. One of the most important components for us is the CMB. Here we have 4 different types of component separation techniques. So the first one is the same I showed you before. So this is a pixel-based Bayesian parameter estimation. This is done in midlet space, internal linear component analysis in midlet space. This is a template-based component separation, and this is instead in spherical analytic space. And so all of these different techniques, they agree very well. Unfortunately, they cannot constrain about 3% of the map where the sky, the emission from the galaxy is too high to be able to constrain it there. So in the map released, 3% of the sky is filled with the constrained white noise realization. Here you see the different types of component separation we have used. They agree very well at low L, at the highest scales. Here you see also WMAP9 is in the plot. So they agree within 1 sigma. Yeah. So here you see the foreground removed CMB. So this is the map obtained with spherical harmonics component separation, and this is the best estimate we have of the CMB at high resolution at large sky coverage, and this has been used for the non-Gaussianity analysis. And from that map, you see here the blue is the power spectrum of the map, and at higher L, this is dominated by white noise. However, by using the Alfring difference that Peter showed before, we can decouple the noise, and the output is a spectrum. It's the gray spectra here, so we can identify 7 peaks, and the red is just a binnet version of that. It's not enough. And so here we show the spectrum again. Here in the error bars we have also cosmic variance, and you can compare the the error bars without cosmic variance and with cosmic variance. So this is including cosmic variance analysis without cosmic variance. So as one of the purposes of the Planck mission was to extract everything possible from temperature spectra, and this is the result. So second, this is the likelihood pipeline. So it's important to understand that we have different type of CMB maps we use for different purposes. So what I was showing you before is the spherical harmonic based map, which is used for non-Gaussianity analysis here, while we have for the likelihood code instead is based at low L on the pixel-based component separation. So the first we saw before with the different components, and this goes at low L. At low L we also need polarization data. Currently, Planck polarization data are not ready yet, so we are using WMAP Q and U polarization at low L. And then instead at high L, for currently the component separation maps are not robust enough for this, so we estimated it was better to directly use the power spectra, so we apply heavy masking, and we use power spectra of just 100, 143, and 217 gigahertz, and their cross spectra, and that goes into the IL likelihood. The likelihood code also includes the lensing potential. And so this code is publicly available, so can be used to run cosmological parameters against the Planck data. So our run of cosmological parameters, here we have the results of CMB plus lensing only, so this is just Planck. And here we have also WMAP polarization, and then IL coming from SPP and ACT and DAO. So just a few highlights. H0 is from the Planck data comes lower than previously. Here we have also NS, which is definitely below 1, and then we have. So from here, the complete energy content of the universe comes out significantly different. So you see, if we are using this is WMAP only against Planck only, there is a significant difference. So about 18% in more dark matter, more baryons, and minus 6% less dark energy. Okay.
Just as an aside, almost to the day, 21 years ago, Peter and I were at a National Academy meeting, trying to debating what to release, and soon after that, we released the COVID data, and then not too long after that, we released our own data from the South Pole and from balloons. So it's been about 20 years since detection started. Now we have this massive data set, which is telling us much more about the universe than simple detections. And I think one of the things to keep in mind here in all this is that the entire story is not told by power spectrum. Power spectrum intrinsically assumes a certain kind of cosmology, namely one that has essentially a random phase component, and that may not be the universe that we live in. In fact, we know intrinsically just looking around, we look around this room, none of you are isotropic by my method of measuring things. You are all quite off the norm, some of you more than others. And this is what we want to understand about our universe. You know, where on the spectrum does it lie, so to speak. So at the moment, we know that NS in the power spectrum does not equal 1 to high significance, and from Planck alone, it's almost 6 sigma. We know that the tensor to scalar ratio, which is usually denoted R, is less than about 10% at 2 sigma. from T alone. And as Peter mentioned, we have not weighed in at all with the really massive power of Planck, which will be the polarization complex. We're not releasing that at all. So what you see today is just a piece of what is about to come in the next 2 years. So if you wait a little while, it'll probably take you that long to read all 30 papers. You'll see something even more interesting. So here's a plot of NS versus R. And you can see NS would have to stretch a long ways to get to 1. There's a variety of inflationary models that can be fit against this. And again, all this is in the context of a standard 6-parameter model, which intrinsically assumes that you extract information from the power spectrum. But in fact, that's the wrong way to look at an experiment like this. You have a massive amount of pixels, which is far more than 6. And yet you're extracting most of the data, decimating it into a few parameters. So please keep that in mind as you think about this, because we're already getting flack from people who don't get it. So here's a couple of selected parameters based on, again, the assumption of random phase. And for comparison, people always want to know, so how did you do relative to the other people? So here's some comparisons. The colorful ones are Planck, and the not so colorful ones are WMAP. That wasn't by design, actually was. And you can see, there's decent agreement, which you would expect. Some things don't agree as well as others, but in general, it's not so bad. But again, this decimates the universe down to a few parameters, and that's the wrong way to look at the data, but it's the way that we need to extract some information. So we do disagree with WMAP in some important ways, and with previous data sets, but we're now getting to the point where we're into quite relatively precise measures, although we did just change dark matter by almost 20%. I don't know if you consider that to be precise or not. But we did make a major change there. So here's a measure of H naught from Planck alone, from WMAP, and from a variety of other external data sets, which are non-CMB. And you can see, everyone's sort of clustering around this region close to 70, but we are significantly low, and that becomes important in just a bit. All measurements of H naught, if you go back through the literature, starting with Hubble, who got it wrong by a factor of 10, but otherwise he was right, are subject to lots of systematic errors. So you should keep this in mind when you look at H naught. We believe that we probably did a better job, but we'll see. So WMAP, last week, I don't know if any of you came to the talk by Roseljak, some of you may have been there. He showed a nice slide which caught my attention, which is the WMAP inconsistency with the baryon acoustic oscillations. And here's a somewhat redacted version of his plot. It's a little bit different than this, but it shows the essential features. If you take WMAP, in this case was 7, but 9 doesn't change much, plus South Pole Telescope, which is a high angular resolution telescope, and a lambda CDM model, you see that these two, this being BAO here, and this being the air ellipses, the 1 and 2 sigma in both cases, they don't really agree very well. And one could argue about how many sigma it is, but it's not a very nice agreement. Now, if you look at the same, so this was 1 week ago, and Bruce made the comment, gee, I wish I had 10 more days here because maybe I could see what happens to this. So now you add the Planck equivalent to this. Now things move down and over a little bit. Now you say, well, they still don't agree very well, do they? But then you ask, well, what went into the BAO estimator here? And what went into it as an external prior was H naught. Where'd they get H naught from? They didn't get it from us. They got it from other indicators. Now, if you take the Planck H naught, which just happens to be right around 67 or 68, and you move BAO over to that H naught, guess what? They're an amazingly good agreement. So what last week was a statement by Gross, who's a theorist, so he can't take any responsibility for the data that goes into it, was that this might indicate new physics, which is true. If there is a disagreement like this, it might indicate new physics. And that's an important distinction when you measure it another way, and you would say, this still might indicate new physics, or it might indicate something's not right. in a data sense. And what's not right here is if you change h naught by adding the prior from Planck, they lie right on top of each other within 1 sigma. So someone asked me, so what's new with Planck? Yeah, I said, I don't know, what do you mean by that? Well, I knew what they meant by that. So, whether you say new physics or not new physics, that's kind of an important question. And what goes into that is what data do you have. So here you have, I think, a quite spectacular change. And that's, again, only in the context of a simple model, just more consistency. One thing that Planck did very well is it actually can measure the motion of the CMB photons around mass. So you can think of it as a gravitational deflection, like the measurement of the gravitational deflection around the sun that was done in the early 1900s. Do the same thing, but using the CMB itself and look for the change of the peaks and valleys relative to various data sets, including the Planck data set, which I'll show you has lots of these. So we see a huge, I've never seen a 25 sigma effect before, although I'm about to show you a 42 sigma effect, which had to be there. I was so pleased we got 42 for the right answer. But this is 25 sigma. So either we got it really, really wrong, or we measured something. It looks like we measured something. So we do see lensing of the CMB by the universe itself.
How do you measure that?
Pardon?
How do you measure that?
So you have a sky, and you look at the sky, you have a map, as Peter showed you, and of course you'd say, okay, I have a map. How do I know it's lensed or not lensed? So one thing you do is you look at it and you say, is it consistent with what you would expect from a lensing potential? Then you say, from what? Well, first of all, Planck measures a lot of point sources. I'm going to show you some of them soon. So you can say, let me have a model of those point sources, and let me see if they're lensed relative to that measured point sources that I have internal to the data set. That's one way to measure lensing. The other way to measure lensing is to take external data sets, optical data sets, X-ray data sets, and say, is there a correlation with the patterns relative to the known positions of objects in the sky? And those both yield a lensing potential. Okay, but I'll show you some more of that in a bit. And again, there's 30 papers out there, so we can't actually like to, but we keep you here for the next 2 years. So this is an example. The number of sources we have is in the tens of thousands of sources on the sky. When we released the COBE data, we basically took a galactic cut and said, there's nothing else to worry about. That's what we did, except for a couple of known bright radios. That was it. There was no other cut. Now we have this massive data set with huge simultaneous. Literally, it would have taken us 1 million years to get the equivalent sensitivity, not including the angular difference, which would have taken, probably 1 trillion years to get there. So this is an incredible difference in 20 years. Look, it's been 20 years. So we have lots of point sources. Those point sources can be used for lots of purposes, such as measuring the sun ISO dosage effect. Here's a list of over 1,000, a visual representation on the sky of 1,000 sources. This is the galactic plane. This is one of the masks that we use to cut out the bright stuff on the galactic plane. And the red blobs are SC sources. And we can talk about how you measure these if you want, but you measure different sources. Sources, galactic clusters with hot gas. The effect is CMB in a specific way. So we measured some that were previously known to exist from X-ray catalogs and optical catalogs. A couple, not very many, were known to exist from CMB-SC. Most of them were simply cross-referenced to X-ray and optical, but were not known to be SC. Now we compare them, we see they are SC sources. That's the majority of them. We found some new ones that were not known to be in any catalog prior to our measurement. So these are blind measurements, which we then went back and said, please look at your catalog, see if you see something. And we saw about 200. And then we found almost 400, which are not in any catalog known, but we find it in our own catalog, and we believe they are SC sources from their signature in the CMB. There's a lot there. So just picking out highlights. So non-Gaussianity. So people sometimes constrain non-Gaussianity by a variety of methods. This is a particular two-point method, which uses a parameter called FNL. And FNL is a parameter that, if it differs from 0, means that you have non-Gaussianity. It's just one way of specifying non-Gaussianity. There's G types, there's tau types, there's a variety of types. So in slow world inflations, you predict a relatively low value, sorry, this should be over here, of non-Gaussianity of about 2%. Now, we are not at that level of sensitivity. Unfortunately, we'd love to be, but this is what you predict. So that's a very low level. And if you get to that level, you don't see something. I always love these things because these are never true. You know, you say that there's never happened, but of course then they just pull out their test for models that I forgot to tell you do 10,000 times lower. Anyway, we measure about 3 plus and minus 6, so consistent with 0, which is 10 times lower than what we had previously from the WMAP, another data set. Also 10 times lower here. Here it's not quite as dramatic. Anyway, we're marching down on both R and F and L. We do have some weird things going on in the data, which we refer to as anomalies, which are interesting because they are very real. Here. Okay, you can also cross-correlate polarization with the extremes in temperature. And if you read through the papers, you'll find a couple of references to polarization, but for the most part, we've sanitized everything so you can't deduce polarization. But there is a plot which you should try to search for, which snuck in after much debate, and I'll let you try to search for it. But this shows a indicator that we do indeed have polarization, very well measured, and we're just showing you a little bit of it. This shows you where we can use the high-frequency information from Planck to look for the cosmic infrared background sources. The cosmic infrared background was first seen by Kobe with the diffuse infrared background experiment, and now we believe that most of the cosmic infrared background is in fact not diffuse, but is in fact due to a collection of a large number of point sources. So we find a lot of these point sources in Planck and other instruments as well. And we can measure lensing deflection from that based on looking at a lot of these point sources. So this is another way that we measure lensing and the CIB together. So this gets back to your question, Stan. Okay. We do see some oddities, and some of these have been hinted at before, but now we really see it at a level which you cannot easily ignore. So there's something going on which breaks, I hate to use the term, but it does break symmetry in the universe. And I don't know why. We don't know why. We thought, all of us thought at first it was all just instrumental with the galaxy, but it does not appear to be true. It appears to be something real in the universe. We don't know what it means, and I'm sure it's going to spawn a lot of papers.
What are we seeing that outside?
You're seeing an artist. You're seeing. It's not an artist. This is a map. This is our map. You smooth it so it's a little bit easier to see large-scale things with the eye. And you notice that one part of the sky appears to be different than another part of the sky. It's not obvious from this at all, so you have to read the paper on topology and isotropy to understand the significance of it. But you would, to first order, look at these very deep blues, which are low-temperature regions, and say, I don't see these over here. Is it a color scale issue? No. Is it truly something which is different between these two hemispheres? The answer appears to be with 3 sigma significance, yes. Why, we don't know.
So what is the gray line defines the hemisphere?
Yeah, well this is just, we're just splitting it in a way where this part of the hemisphere looks different than this one. It's kind of like ecliptic.
That's the split that maximizes the effect.
This is okay. So, yes, if you want, yes. You want to answer yes or no? Yes.
And then find direction of a gradient.
Right.
Direction of a gradient.
Yes. Okay. So I mean, yes. The problem is that in order to really do this justice, you'd have to understand the statistics of what went into this. What appears to be true is that there is something which is breaking the symmetry, and I think it's a reasonable way to state it, that you don't see a symmetric up, down, right, left, universe. Yeah, the problem with, of course, isotropy is what are we measuring with this instrument? Anisotropies. Okay, so the very statement of isotropy always struck me as odd, but yes.
Well, Gaussian fluctuations and
Yeah, well, so that's yet yes. Yes and no, right? So that's yet another difference. Is it Gaussian and not isotropic, or is it non-Gaussian? Of course, you would look at this as I would and say this probably indicates non-Gaussian. But then when you do the non-Gaussian test, by other means you say no.
Well, I would look at this and say, what is the significance?
3 sigma, 2.7 sigma. So you could argue
For what?
okay, for a statement that you break isotropy.
With a dipole?
Yes.
Dipole.
Dipolar-like breakage, except it's really more complicated than that because it's L by L. So if you go to low L, you see a difference between the low L power spectrum from L of about 10 to 30 versus the high L power spectrum where you don't see this effect within R sensitivity. You do see a 3 sigma effect at low L, and you do not see a high L. What does that mean?
A dipole is pretty low.
Yeah, but it's not an L equals, it's not a dipole, it's a dipolar-like effect. It's not a dipole effect, it's not L equals 1. It's L between L equals 10 and 30. You know, people try to fit in Bianchi models, which are nice, you know, they have nice non-isotropic portion. Okay.
It's a dipolar effect in what direction?
So let me actually answer that by this, but this is not the answer to what you just asked, but I'll answer it differently. So then suddenly, the question is, there's a difference between the sort of southern ecliptic sky and the northern ecliptic sky. I wish we had it to 20 sigma and I could do some more justice, but we have to about 3 sigma. If we measure the difference. What we do see is something which breaks symmetry in another way, but in a way that's reasonable to break symmetry. If you move, like in Star Trek, and you hit the warp factor button, you know, you see the sky certainly go beautiful in front of you, and they don't ever show the backwards direction. But you can imagine the same thing happening in the universe where you say, well, we're moving through the universe, aren't we? So don't break symmetry that way. Shouldn't we be able to measure it? And we, of course, have measured this effect at the level of bar about 0.1% the speed of light. That's we're moving about 300 kilometers per second relative to the CMB. So here you see what happens if you increase this factor by a factor of 700 to about 0.85 C. This is what the sky would look like if you do this. You missed the good part, the H0 part. So, it's all right. Our real speed is about 0.1% the speed of light, but you can still look for the effect. Now the effect would be estimated to be 10 to the minus 3 of the anisotropies, which are 10 to the minus 5. So you're looking for a 10 part per billion effect. Well, I don't know about you, but 10 parts per billion would be a pretty, that's a lot of decimal places. So, on the other hand, we have nanokelvin sensitivity in the instrument. We can measure part per billion if everything worked well. So, do we see it or not? And the answer, amazingly, is, not amazing, but I was very pleased, we do see it. And we see it at greater than 4 sigma, which implies something very interesting about the instrument, and implies something very interesting about what you derive from the instrument, because we are now able to say with reasonable certainty that we are stable, at least on large scales, to better than 10 part per billion, which is an amazing statement for anyone who knows anything about this field. 10 part per billion of 3 Kelvin, that's incredible. And we're better than that. We're actually a few part per billion. So this is showing the direction of the measured dipole from the dipole to CMB versus the measured effect from the aberrations, which are the splitting of isotropy from that motion of the power spectrum. It appears we see that at greater than 4 sigma. Okay, so I want to try to terminate so I can go on to Jatila here. Just in summaries, so if you reduce the millions of pixels we have down to 6 parameters, we don't see anything particularly new. But that's, again, under the assumption that the universe is nicely described by random phase. We do see a lower H naught that's significantly lower. And if you use that H naught with excellent agreement with BAO, if you use the WMAP H naught, that you don't have good agreement. So take that as you will, but we think it means that we probably got a better answer. We don't see any neutrinos implied beyond 3. From the CMB alone, you have implied dark energy goes down by about 6%, and baryons go up by about 9%, and dark matter goes up a whopping almost 20%. significant. Now, if you include external priors, such as optical data sets, supernova, etc., the difference is not so dramatic, because now you're introducing lots of other priors. So it's still a significant change, but not as whopping as the CMB alone. It looks like we're flat to within 0.1%. We have a neutrino mass limit, which actually somehow didn't stick very clever. It's 0.66 eV at 2 sigma, which is not that spectacular, but still interesting. It's better than before. We see the running of the spectral index to be more or less consistent with no running, but there is, almost a 2 sigma effect, so I'm not too worried about it yet. Spectral index is not unique, it's almost 6 sigma. No evidence for dynamic dark energy or variations of constants yet. Hopefully it'll be there someday, but that's it. There's some tension between matter fluctuations from the CMB and those implied from SZ. The power spectra that you would get from CMB versus from SC. It's probably from SC modeling, that's our best estimate at this point. You do see about 3 sigma estimator for low L intrinsic deviations from isotropy. Again, this is an oxymoron if I ever heard of it, because we're looking at deviations from isotropy from anisotropy. But it is what it is. This is consistent with simple models of slow roll inflation. We see a 25 sigma detection of lensing. We see a 42 sigma detection when you cross-correlate the CMB with the CIB, which we measure. That's a huge number of sigma. Maybe you're not impressed, but I was. We do see measurements of the CIB power spectra all the way down to about 200 gigahertz, which constrains dark matter halos and high redshift. It's interesting. We had the first all-sky SC map and power spectrum. Sigma 8 is about 0.8, so this is reasonably consistent with what we've seen before. And we had the first, I think, decent detection of the integrated Sachs-Wolf effect at about 3 sigma from the CMB alone. And you imply the omega lambda from the CMB only 0.7. Okay, so I'm going to turn this over to Jatila, and then we'll come back and wrap it up with more stuff.
Big question.
Yeah, well, I will.
Do you want to take the question now? Or
No.
Okay. So,
Hope they'll get it.
NASA takes very seriously the education component of all its missions, and so I've been the education project manager for the NASA collaborators on Planck for, I don't know how many years, 5, I think, or 6. Anyway, this shows, this is our webpage, the main Planck page of Caltech. It shows all of the people who contributed, collaborated, and we have a significant portion of that here at UCSB. So I'm just going to briefly go through this. We have a number of really cool simulations, which are available through our webpage, and I'm not going to demonstrate them for you now. We don't have time, but I'm happy to show them to people and give them to people who play within their classes. So one of them we call the Planck mission in virtual reality, and basically it runs its Planck with the actual orbital data running in a virtual solar system, and this is the opening screen. You have a few different options. And you go in and you can fly around. You can zoom in, you can zoom out. Very useful for actually, you get that feeling that you're really flying around, even more so than in the planetarium where it's all Earth-based. You're actually on a, you can change your reference frame in the simulation. So it's pretty cool. You have all the different backgrounds in there, and of course now we'll put in the new background. And I started working on this when I was teaching at Purdue, so these were my collaborators at Purdue at the Center for Visualization and Simulation. Then we have this visualization and sonification of the CMB. The idea being that, of course, the very early universe, before there was any structure, was just a ball of plasma filled with these very long wavelength acoustic waves. The longest one about 40 to 50,000 light years, which is a frequency of something like an order of 10 to the minus 14 hertz. I did the calculation. It's something like 47 octaves below the lowest note on the piano, which is 27 hertz. So we've done effectively a 50 octave compression just by taking the angular wave number on the sky at the first peak, which is around 0.9 degree, and mapping this L of 200 to 200 hertz, and that turns out to be effectively a 50-octave compression, so you can hear it. And this is a simulation that runs on your desktop that I've been working on with students of Professor Joanne Kuchera-Morin, who works upstairs. She's the director of the Allosphere project. Their main thing is multimodal representations of multidimensional data sets. And so I've been working with your students, Ryan McGee and R.J. Duran, and a few others who have since left. So we actually have an interactive version of this that is coming up online. So let me see if I can get the Chrome. And you can actually play it in Google Chrome. It's very cool. You can well, I guess I can't make it wider on this, but off to the right, which you can't see on here, there are actually sliders where you can change the harmonic contents. You can listen to someone else's computers, like computers and dances and child. So you can change the bandwidth. And you can hear the harmonics. The high frequencies, you're basically listening to, I guess we should have word that. It's about what Kobe would have heard. So we get down to that, and then we add in one. Okay, so this was originally built as as a standalone simulation where the user can input their own models of the universe, and you're playing with the different density values. And basically it takes 15 models and you can make them yourself in CAM, and there's a whole curriculum package to go with it. So then we have one more. This is an interactive display for museums and science centers that I created with a student, Laker Galia, from the Geography department, who also works in Phil's lab. And it's actually currently installed in the Santa Barbara Museum of Natural History Planetarium. Has a bunch of interactive maps. These you press on these and you get the full explanation. This is an interactive map where you can zoom around and make yourself see. This is a slideshow with voiceover and music that I created where I try to sound really cool. And I have actually original music that I mixed in those for permission to use. And then these are videos that were provided by other collaborators. And it's designed in such a way, it's programmed in HTML that any idiot can program it, including me, and you can change it for your own use. So those are basically some of the things that we've been working on here in terms of education and outreach that are available for people to play with. Okay, so now we turn it back to who's doing wrap up? Bill, are you doing wrap up?
Oh, sorry. So I just want to quickly go through a couple of things, then we'll take some questions. So first of all, as I mentioned, there's a lot more data to come. So we already have the data in hand, and it's not that we're rolling it out to keep the funding agencies funding us. Actually, no, we have to understand it. We want to make sure we understand it properly. It all looks good, but we have some things we want to check first. So one of the major hammers to come is polarization, which we're only hinting at now. We have twice as much data for the high-frequency instrument than we're releasing today. We have 3 times the amount of data for the low-frequency instrument. And we're still taking data with the low-frequency instrument. The high-frequency instrument has run out of helium gas. Okay, so in 2014 and 15, we'll release polarization, the additional HFI and LFI data. We still have more coming in on LFI. We'll have much better estimators using polarization. We will have a better measure or limit on R. We should get down to about 0.05 at 2 sigma. So that's getting into extremely interesting territory, which we are already entering. we'll have a better measure limit on various inflationary models, and we'll have a lot more point sources SC at others. So there's a lot coming. Oops.
It's just a recap. That's available.
Right, okay, so I just want to make sure that... Okay, so we'll release basically what we've shown you, but in a lot more detail, and all of these will be enhanced significantly when we include the additional data plus polarization. Okay, so there are, as Peter mentioned, there's 29 papers, which are a huge amount, and a little advertisement for the K2P. It just so happens in a week and a few days, there'll be a primordial cosmology workshop, the 1st of April. So the timing was good. Of course, we kind of knew what the time was going to be, but it's still good anyway. And then at the end of that, there'll be actual
I have been spotted for 2 years.
Okay, so thank you very much. We'll entertain some questions, we the group, and appreciate you coming and listening to us. Thanks.
So, the low L scatter around, how severe? Do you have a way of summarizing if I take an ensemble of universes, how often will that happen?